And I'm Brian.
And this is Two Skis Walk Into a R, where we're this time going to talk about non-parametric tests.
Why would we even use a non-parametric
Well,
test?
that takes some explanation, doesn't it? ANOVA, our old friend ANOVA, requires those assumptions, right? That the residuals be normal and the residuals be homoscedastic.
That's correct.
And sometimes you just can't transform your data to meet those assumptions.
Yeah, sometimes data have an extreme amount of zeros, and if you have a lot of zeros, it hardly ever will fit those transformations.
Yeah.
Sometimes you just have strange distributions from the populations that you sampled.
Yeah.
And it's a requirement of the ANOVA to meet those assumptions, otherwise we can't trust those p-values because It's based on a mathematical relationship with a normal distribution.
Yep.
If it's not normal and not equal variance, we're out of luck.
Yeah.
Or are we?
Well, we're not out of luck, right? We're out of luck with ANOVA, but we're not out of luck because we have a non-parametric test. So we're going to get to that now. So just to set this up, we have two previous videos, one that did a straightforward ANOVA on sepal width versus species and did not require any transformations at all. If you haven't seen that, you have to start there. The second video in the series looked at the petal width, and there we did find that a square root transformation allowed us to do that ANOVA. This time we're going to do petal length, and the real secret is we actually could probably transform this one as well, but we're going to kind of pretend like we can't.
Tools.
Yeah, we need teaching tools. So this is a teaching tool. So we're going to do petal length, and so again, if you haven't seen those previous two videos, you really just have to go see them and then come back to this one. But here we are. I've already got my script up here. I kind of cleared some things out. Can get our data back in there. And then I am going to start by copy-paste adjusting. So I'm going to copy this first ANOVA. I'm going to scream it down to the bottom. I'm going to paste it here. And now this time, though, I'm going to change it. So we're going to do petal length, right?
Mm-hmm. So before we jump into the analysis rate, for this Kruskal-Wallis test, this non-parametric test, does species still need to be a factor?
It sure does.
Okay, so a lot of the same data structure that we use, that we set up for an ANOVA, is going to be directly applicable here to our non-parametric test.
It is, which is really nice. So now let's change this from sepal width to petal length. And again, I'm just going to copy that petal length, and I'm going to paste it in the places where it needs to get pasted. So let's look at this. Oh my gosh, I think the odds of getting data like this, assuming there's no difference between them at the population level, is super tiny.
I would say so.
So there it is. You could go ahead and make this statistical object. You could get the summary on it and stuff like that, but we know it's not going to be a valid p-value. So let's just look at this. That doesn't look terrible.
Doesn't look terrible.
No. So Shapiro-Wilkes pretty happy. But that looks pretty heteroscedastic, and the Bartlett test fails miserably.
Mm-hmm.
So typically you would then go p-value not valid. As we showed you in the previous video, you can do the transformations, and you keep trying transformations until it works. And like we said, hint, hint, if you really did try all of these transformations, you would find one that worked. But let's pretend that we couldn't. And that happens with real data all the time. Does that ever happen to you, Brian?
It happens to me more times than I'd like to say.
Yeah. So this is not an infrequent occurrence.
Especially with ecological data.
Oh my gosh. It's the ecological data is the best and the worst of the data right there. Okay, so if no transformation is successful, you will use a non-parametric alternative test and or speak with a friendly statistician such as your instructor or me or Brian, or whoever. If you want if you really want to go crazy, you could talk to Tim O'Brien.
So I got just a quick question for you, Ray. Why don't we just use a non-parametric test every single time?
Oh, wouldn't that be great? Because then we wouldn't have to do all this assumption testing stuff.
It really seems like if this is our escape plan, why aren't we just always using the escape plan?
Man, because sometimes escape plans aren't as powerful as the normal plan. Yeah, so it turns out that for the same amount of data, you're less likely. And now, correct me if I'm wrong, because I'm like 90% on this, but only 90%. to say that this non-parametric test, it's less powerful. And so that means that given the same data, you're less likely to find a statistically significant difference than you would with a ANOVA.
Yeah, so I think as we think about what the non-parametric test is doing, we are really not using the power of the normal distribution.
The power of the normal distribution is a phrase.
And not a statistical power in this context, just the literal power of the normal distribution. So we have the ability with that normal distribution in a parametric test to be able to... Like an ANOVA. To be able to more easily detect statistical differences because we have this assumption of a normal distribution and equal variance.
Powerful normal distribution. And if you could see Brian's hands, he's drawing normal distributions in the air, bell curves, the whole thing.
But the Kruskal-Wallis, this non-parametric test, doesn't rely on that underlying distribution. Without getting too into the weeds, it's harder to detect significant differences because we are just not using as much information as we have for the parametric test. So this is just a way to do it. It's still valid, but it's just harder to detect differences between the means.
Got it. I love it. So this is step 6D, non-parametric test. And so Kruskal, it's actually the Kruskal test. That's the one that's kind of built in. And this just takes a y tilde x kind of thing, response tilde predictor. And so that's iris.df, $, and now we're doing petal length, tilde, iris.df, $, species. And that's it. Like, I'm not even making an object over here. Like, I'm just running this thing, and it's got its output built into it.
And it's still similar form of the code that we use in ANOVA.
Yep, and I got to look at the raw data graph when I'm comparing
Bring up that raw data graph.
Right. So this is saying that according to the Kruskal-Wallis test, your odds of getting data like this, assuming that these samples are drawn from populations with equal means, is super small.
So Ray, one thing that we can do, as good coders do, can we write out and describe the null and the alternative hypothesis next to the Kruskal-Wallis?
Oh, sure. We can.
It's a good habit. It's a good habit to get into, especially as you're learning these different statistical tests.
Right. So means of different species are the same at the population level. I think I'm doing this kind of weird. But is that all right?
I think I'm pretty good with that.
Okay. Yeah, I kind of get a little sloppy with this stuff sometimes. And then the alternative is the mean of at least one species is different from the others.
Always good
at the population level.
Comment that code.
Yep. And then it saves you from some confusion. So, right. So they're probably different.
Looks pretty different
to me. And then really to do a proper analysis, we would also need to analyze, it looks pretty clear that Setosa and Versicolor are going to be statistically significant different. I bet these guys are too, but there's a chance that they're not. So when you're doing an ANOVA, you do this Tukey test to do a post hoc test. The analogous post hoc test is called Dunn test. And to get the Dunn test that I like to use anyway, I don't know about you, I need the FSA package. So I'm going to, and I've already, installed that from the internet. So I just need to get it up and running in working memory. So I run that guy, scream it back down. And now I'm going to do Dunn test. That's the one I want. And I believe it's just this guy. And I'm going to hit run. Boom, there it is.
Look at that.
And so it's got an adjusted p-value that's sort of adjusting for the fact that we're doing multiple comparisons. But if you look at these are all, some number times 10 to the minus 9th, some number times 10 to the minus 29th, which is
very, very small.
Incredibly small. So, so indeed, all of these are statistically significantly different from each other.
So just to summarize here, as we think about running our statistical tests when we're looking at categorical data, these 3 iris species, going through the ANOVA workflow, and if it needs a transformation, to then do that transformation. If your transformation is just not cooperating and you can't meet the assumptions of those statistical tests, we use our escape valve with the non-parametric test, the Kruskal-Wallis, and then the multiple comparison of the done test.
Yep. Beautiful. Nice summary, Brian. I love when you summarize.
Thank you.
Makes me so happy.
I'm glad.
Okay. I think we're done.